Good morning and welcome. Oh my gosh, this is so fun. Best YouTuber. Hey, I appreciate that. Thank you so much. Fun fact, if you can, should I even say this? Sure. I also am a YouTuber I technically have two channels, one that I made in middle school and one that I made in high school. Yeah, it's funny. But no, I appreciate that. Thank you so much. I have a total of 16 subscribers on my YouTube channel right now, and that's all 16 of you. So thank you if you subscribed. Make sure to like and comment, but there are no comments because I turned them off. I'm kidding. So anyways, good morning, welcome. I hope everyone is doing well. It is Wednesday. Yes, the middle of the week. I know we are all tired. That is why I have my coffee every single morning. Fun fact, before prep started, the last time I had a cup of coffee was about a year and a half ago. I've had coffee every single day during prep. If that is any indicator of the amount of time that I know all of you are putting in, and me as well, right? But no, that's awesome. Thank you all for showing up. It looks like we are all just about here, plus or minus a few of us. Let's talk really fast about what we're going over today and yesterday. Number one, section 2.4, I said I would come up with a handwritten problem. I have not done that yet, and I think it would just be better if we focused on the problems from 2.5, right? 2.4, if you really want to submit a problem, go back, look at the notes, okay, and just try and let me see if I can get you a page number for that, okay? So if you want to go to page 2.4, if you go to 2.4, section 2.4, page 107, right? If you want to do example one, you can. It's not required, okay? So if you want to do example one, I can grade it for you, right? And that's working through the whole proof. Remember yesterday we only like set it up halfway. We found epsilon, right? But we were going to solve for delta, but we just ended up solving epsilon. So that's page 207 or 107 and 108 in your textbook. If you'd like to do that, I will be more than happy to grade that for you, so I can be like, yep, you got delta epsilon proofs, you're good to go. Or I can provide some feedback. Otherwise, not required. Again, I'll let your Math 1A instructors go into a little bit more detail on that. The other thing too is because, again, at the end of the day, you're going to get 1 or 2 questions max on your midterm/final about that, and the rest of the questions will be derivatives, integrals, all that stuff from there on, and so on and so forth. And I'm much more concerned about getting to that material than I am spending 2 days on like one question that'll show up in your test, if that makes sense. So other than that, the homework problem or the homework assignment I will post tonight, that will also be due Saturday at midnight. So all of your assignments right now will be due Saturday at midnight, even the ones that I assign on Friday, right? So this Friday, it'll be due on Saturday. So you'll have 1 day to do that. The goal here is to try and do your homework assignment every night, right? And then submit it that night. But I'm giving you all until Saturday because we talked about that last week. And I think that would help everyone just with timing, right? And it helps me with timing too, to give myself some time to grade things as well. All right, I'm joining on my iPad. Oops. Okay, so I'm going to share my screen. Let's talk. What are we going over today? Theoretically, or technically speaking, nothing new. However, I would like to go a little bit more in depth about chapter 2.5. Number 1 from 2.4. No, so not number 1 from 2.4, example 1 from 2.4. So it's not the problem, it's not in the problem section, it's in the example book from, it's on page 107 and 108 of your textbook. So it's technically it's in the lesson. So it's example 1 in the lesson of section 2.4 before you get to your problems. And you'll notice it's the exact same example that I gave in class yesterday. It just goes all the way through. So if you want to attempt it on your own, right, and then check your answers and submit it, that's totally cool too, and I'll give you some feedback on it. That's all I was saying. Cool. It looks like just about everyone showed up. Maybe there's like 2 or 3 people still sleeping. That's fine. Hopefully you are watching this YouTube video right now, and we are all saying hi to you because we all miss you in class. But no, anyways, section 2.5, let's talk about it. Let's jump. Oh, first, I said this would be review. So any questions from any of the last sections, like anything. I mean, I'm talking domain, range, limits, functions, inverse functions, anything. This is the time where you can ask in class and we can all go over it in depth, in detail, and I'll come up with problems. 2.3, all right, I'm flipping my book to 2.3, 2.3 specifically. Is there a specific thing of 2.3 or just 2.3 in general? 2.31, question number 1 in 2.3. Okay, yeah, okay. 2.3, so this is our, awesome. This is going, let's talk about our limits, right? These are interesting. These are our limit rules, okay? So if you remember, I had that picture put up and I said, copy this down if you can. If not, it is page 95 of your textbook, right? So make a note of this. This is our limit laws. This basically is just telling us how we can, like, how we can take our limits and manipulate them based on what we're given. So problem 1 basically says this, right? The limit as x approaches 2, as x approaches 2, yes, that is an arrow, of f of x is equal to 4. Okay, so f of x, the limit as x approaches 2, that equals 4. The limit as g of x approaches 2, or g of x as x approaches 2, that's equal to -2, right? So this is what's given to us. So we don't have to find it, right? We just know that this is what it's telling us. That's equal to -2, right? And it's telling us that the same thing, right? For h of x, okay, that is equal to 0. Limit as x approaches 2, okay? 3 functions, okay? We have 3 different functions here, f of x, g of x, and h of x. Do I know what they look like? No. Do I have to in this problem? Not at all, right? Because we are asked to find the limit that exists. If it doesn't, explain why, right? So A, B, C, D, E, F. I'll just go through each and every one of them pretty briefly. So we have A, part A, is basically telling us, all right, we have f of x plus 5 times g of x, right? That's part A. I will do this. All right. And it is telling us, oh, I apologize. That is not 5, or yeah, it is 5g of x, never mind. And this is the limit, right? As x approaches 2, right? Of this whole thing now, right? So we're like, oh no, what do we do? It's not too bad. Basically, all we do is this, okay? Do we know what the limit as f of x approaches 2 is? Yeah, that limit is just 4, right? So we can break it up separately, right? We can apply this limit to this, and then we can apply the limit to that, and we can add those together at the very end, right? So think about like our multiplication rules. If you kind of think about like multiplication, right? If you have a binomial, right, and you have like something on the outside of that, you can apply it to each term individually, right? Kind of like the FOIL method. So same kind of thought processing applies here. So you're like multiplying that limit of f of x, but it's not multiplication. You're taking the limit of f of x and g of x respectively, right? So this ultimately becomes the limit as f of x approaches 2. I'm going to write that down here. That is simply just 4, okay? Now, forget about this 5 for a second. What is the limit as x approaches 2 of g of x, okay? Well, it tells us up here, right? In our given initial, oh gosh, there it goes, it disappears. We're back. The limit as g of x approaches 2, that's -2, right? So we already know this is -2 right here. So I'm just going to rewrite it like that, -2. But what's the only difference here? It's 5 times -2. See that? So this is 4 plus 5 times -2, which is -10. Okay, 4 plus -10, that is equal to -6. Problem solved. Any questions how I got part A? Anyone have any questions, or does that make pretty clear sense, right? We're just dealing with notation, right? I think if you've never seen limits before, then you're just kind of like, what do I do? It's a little weird, right? If I gave you a simple problem that was like, that I was like, okay, you have the limits, or if I was like, all right, you have 5 times x plus y, right? And I said x equals 2, oops, I said x equals 2, and that's a 2. I'm sorry. 2. All right, here we go. I'm drawing it slowly this time. There it is. Boom, x equals 2. Still a poorly drawn 2. And y equals 4, right? Let's say just y equals 4x, okay? Then this becomes, oh, well, I guess it still gives a number. Never mind. Let's just make y equal to 4, okay? Then you get, this is 2 plus 4 on the inside, right? Times 5 on the outside. Then you could either combine like terms on the inside. I think you would have to in this case, right? 2 plus 4 is 6. 5 times 6 is 30, right? Or you could do it individually, right? 5 times 2 is 10. 5 times 4 is 20. 10 plus 20 equals 30, right? So it's the same concept. We're just applying limits to it now, right? I'm going to not go through all the other problems because hopefully it should make a little bit more sense. Hold on, let me check the chat. Yeah, it seemed to, yeah, it really is, right? A lot of calculus is it logically makes sense, okay? And that's what's beautiful about calculus and the rest of math is logically it makes sense, right? And that's the best part about calculus, and that's why we as engineers, that's why calculus is used so heavily in everything, because we take these complex situations and we just turn them into something that logically just makes complete sense, and it's awesome. So the only other thing that I will do here is I will take the limits as x approaches 2, okay, of g of x over h of x, okay? We said, okay, that's an h, not an L, I know. Oh gosh, okay. We said g of x was -2, right? The limit as x approaches 2, we said that was equal to -2, right? That's just our given problem, right? And the limit as x approaches 2, that is a 2, of h of x is equal to 0, okay? Again, we plug in these two values, right? We get -2 over 0, okay? This limit is undefined, right? This limit does not exist. Why? We have that 0 in the denominator, right? Anytime you see 0 in the denominator throughout calculus, always think, hold on a second, what, like, something's not adding up here, right? So that is the only time where we can't take the limit because it's undefined, right? And you're like, wait, didn't you say way back when that anything over 0 is equal to infinity? Sort of, right? Yes, that's true in terms of thinking about it in the abstract way, right? But you'll see as you get into further along in Math 1A, right, towards the end of Math 1A at Berkeley, especially at Math 1B, right, you'll see when you get to series, all that stuff, you'll have cases where you'll actually get a finite number. And what's really cool is tomorrow we're going to start talking about those cases actually. So stay tuned for that. Where do we get the limit? Okay, where do we get the limit of x is equal to -2 and 0? Where do we get these, right? These values? That is given in our initial problem, right? So I stated up here, right? I said the limit as f of x approaches 4, the limit of g of x as x, or f of x, g of x, h of x as x approaches 2 for all of them. These are the values we get: 4, -2, and 0. Okay, we didn't solve them. It literally just said it in the initial problem on the textbook. Okay, so all I did was read the problem, take those numbers, and then just put it on paper. That's all I did. Okay, then we took the equations that we were given and we just inputted those numbers. That's all we did. Hopefully that clears things up a little bit. A limit still exists if it equals to 0, right? Good question. Let's talk about that. So there's two equations. Okay, so if you look at section 2.3 in your textbook, it's problem number 1. So we were dealing with f of x, g of x, and h of x. That's what it gives us in the initial problem. So there's 3 equations, but for part A, B, C, D, E, F, right? So there's A, B, C, D, E, F, okay? We were working on part E, okay? So that was part E of 2 section 2.3, number 1, part E, okay? And that was just the limit as x approaches 2 of g of x over h of x, okay? Okay, I also got another really good question in the chat. it said a limit still, does a limit exist if it equals 0? Let's talk about it, okay? Let's talk about this. Is really good. Okay. Let's talk about our graph 1 over x, okay? Do we know what this looks like? Of course we do, because we are math wizards, and we know exactly what this graph looks like without even having to go to Desmos and cheat. I'm kidding. If you use Desmos on any of your homework assignments, I don't blame you. Some of these graphs can get really confusing. If you have no idea what Desmos is, check it out, desmos.com. Super good app for graphing. Okay, this is y equals 1 over x. Okay, this is just the graph y equals 1 over x. Okay, forgive my poorly drawn graphing and stuff, but let's talk about what happens if the limit equals 0, right? Let's talk about the case where the limit as x approaches infinity, okay, of y of 1 over x, okay? So in other words, as x is approaching infinity, right? So this is our x, okay, and we're going on. This goes on to infinity, okay, infinity and beyond. Does it ever reach infinity? No, but it gets. I mean, we're taking the limit, right? That's why we take the limit. If you want an argument as to why it can never equal infinity, okay, let's say x equals infinity. What about infinity plus 1? See what I mean? Infinity plus 1 is also infinity, but it's still greater than the infinity that we defined. Therefore, we can never define infinity as equals. So there's your brief your philosophical argument for why x can never equal infinity. So anyways, back to this, right? The limit as x approaches infinity, okay? Plug it in, 1 over infinity, okay? In other words, 1 divided by a massive number. Does anyone remember how we were kind of like trying to prove that 1 divided by infinity is equal to 0, right? Basically, I said, okay, let's take a number that I know is very, very large, okay? I said 10, right? 10 is a large number, okay? I'm kidding. So 1 divided by 10, that's 0.1, right? 0.1, okay? Then I said, you know what? Let's try an even bigger number, 100, okay? 1 divided by 100, right? So the bottom number, the denominator is getting larger and larger, right? We're getting closer and closer to infinity. I said, oh, that's 0.01, okay? Then I said, let's try let's try like 10 times 10 to the 100th, okay? This is a massive number. If you want to write it out, go for it. You'll be writing 100 zeros after that 10, and it'll probably take you like 3 minutes, okay? The point I'm trying to get at here, this is 0.01 times 10 to the, oh gosh, negative 29 or something, negative 29 or 30. Do you see how this number is getting infinitesimally small, right? That basically tells us as we take this and divide it by infinity, okay, we get 0. The limit as x approaches infinity of 1 over x, that is equal to 0. Does this limit exist? Yes, okay, it approaches 0, right? And we can see by this graph, right, it's getting closer and closer and closer to 0. So that tells us, yeah, the limit exists, okay? And likewise, right, if you were to plug in 0, you could see it goes off to infinity. So the reason why you can't do that in that case is because the limit of f of x over h of x, right? F of x over h of x, okay? You're dealing with 2 separate functions here. So we might know what the limit is for this one, but if the limit goes to 0 on this one, okay, we said that limit is 0, okay? So in other words, let's say we have something like this, okay? This is h of x, okay, as x approaches 2, right? You see how that's 0 right there? Now let's say we have g of x, okay? G of x, or f of x, I'm sorry, f of x. F of x does something like that, right? So let's say that's, well, technically it'd be negative 2, okay? So I'm just gonna do something like that, right? Yeah, do we know what the limit is all as x approaches 2? For the top, yeah, that's just negative 2, right? Do we know what it is for h of x? Yes, that's 0. Negative 2 divided by 0 is undefined, okay? And there's a very clear difference there. The difference is we are now dealing with 2 different functions, and when we divide those functions by each other, we have to be careful, right? And that's where L'Hopital's rule comes in and all this other stuff, okay? So two very clear differences. If we're dealing with just one function and it goes to 0, yeah, that limit exists. If we're dealing with a function divided by a function and we have 0 in the denominator, that's undefined and it doesn't exist. And we have to use other processes that we'll learn later on how to solve that. Great question. Other questions for me before I jump back into 2.5 and talk about the intermediate value theorem a little bit more. Any other questions? Can be about anything related to math or somewhat related to math. Can we go over 2.2 number 32? Yeah, 2.2 number 32. See, this is really good. Hopefully all of you are able to make it to office hours. If you are going to office hours, I believe Alex is holding them every day this week, and I think Brandon's there too. There is my office hours. Here's the thing. I still see a few people showing up to my office hours right at 6 o'clock every day. My office hours are in the morning. So I'm here from 8:30, well, more like 8:40 in the morning until the start of class. So if you want to come ask me questions, come before class starts and I'll be here 20, 30 minutes early. Otherwise, I'm going to try and hold like a 1 hour office hour on Saturday if people want it. So if you would utilize that office hour on Saturday, right? Because I know it's hard during the week because everyone's busy with everything. If Saturday would work for you, I'm more than happy to hold office hours on Saturday. Okay, so just shoot me a message in the chat, be like, yeah, that's great, let's do Saturday. If not, that's okay too. Just let me know so I know how to plan for that. 2.2 number 32. Let me go to it really fast. I was flipping back and forth. Oops. And then someone wanted me to do a little bit more factoring. So yeah, I'll do a little bit more factoring. So 2.2 number 32. 2.2 number 32. All right, I said that like 3 times in a row. Should I say it again? 2.2 number 32. I'm there. The limit as x approaches 5 from the left. Okay. Right, remember we talked about that notation. That negative sign just means coming from the left side. All right. If you're watching my screen, that's from the right. The limit coming in from the left side. There we go. It's flip-flopped. It's mirrored. All right, of x plus 1 over x minus 5. All right, and it wants us to determine the infinite limit. All right, if we plugged in 5, right, we would get 6 divided by 0, which is undefined, right, or infinity. And so we're just like, okay, how on earth do we start this? Question, if we're coming from the left of 5, all right, let's just look at let's think about this logically, right? Here's the number 5, here's the number 6, here's the number 4, okay? What numbers are to the left of 5? Someone just type in the chat, 4.9, right? 4.9, 4.8, 4.7, 4.99, 4.999. Guess what? 4.99999, right? I could say this. I could say a whole bunch, right? I think you see where I'm saying, right? This is 4.5, 4.8, 4.9, 4.999, 4, right? So we're coming in from the left side, and let's just start there. All right, let's start right there. Let's pick a number. Let's just say 4.9. Okay, that's a pretty good guess. Now let's approximate this, right? Let's plug in 4.9 for x, right? Because we're approaching 5 from the left side. Okay, so plug in 4.9 everywhere we see an x. We have 4.9 plus 1 on the top. Okay, in the bottom here, we get 4.9 minus 5. Okay, 4.9 minus 5, is that negative 0.1, right? Hopefully. Can someone agree or disagree, right? Negative 0.1 in the bottom here. So I should have 5.9 on the top. Okay, so just reducing, this is 5.9 divided by, yeah, sorry, that's 9. 5.9 divided by 4.9 minus 5, which we said was negative 0.1, right? Negative 0.1. Okay, let me grab my calculator, handy dandy calculator. What number is this? And divided by, we get 59. Oh, I could have done that, sorry. We get the number negative 59. Okay, how do we get an even better approximation? All right, well, we said 4.99 now, okay? Now plug in 4.99, okay? So I'm gonna leave that negative 59 there. Okay, that's one of the values. Now let's get even closer, right? 4.99, much, much closer to 5 coming from the left side. All right, 4.99 minus 5 on the top, all right, or on the bottom, sorry, the denominator. Now we have 4.99 plus 1 on the top. Okay, we get 5.99 on the top divided by, now we have, sorry, I'll leave that negative 59 here. 4.99 minus 5, that's negative 0.01 on the bottom. Okay, multiply the top, you get negative 500, or you plug this into your calculator, right? Negative 599. Okay. All right, let's pick 4.999. All right, just so we can get a good approximation, right? 4.999, right? Plug it in. Okay, what do we get? We get negative 0.001 on the bottom, and we get x plus 1 on the top, right? So I'm just doing the math in my head. Hopefully you're following along, right? If you want me to write everything out, I can, right? I'm just plugging in 4.999, right? 4.999 minus 5, negative 0.001. That's how I'm getting these numbers. I'm not just pulling them out of thin air. Hopefully everyone's with me. Plug it into the top. You get 5.999, right? Because plus 1, that's 5.999. All right. Again, go through this, divide it out. We get negative 5,999. Okay, question. What do we notice here? We notice a pattern, right? This is getting larger and larger and larger, right? Does someone in the chat want to tell me what this limit is going towards? Anybody? Anybody in the chat? Negative infinity. There it is. Okay. That's how you would solve, that's how you would approach this problem, right? That's really good. Negative infinity. Okay. So as you can see, right, we can plug in an infinite amount of 9s, right? We can say our x value is 4.999999999, right? We can go on for, oh my gosh, right? But you can see the pattern as we're developing this, right? Negative number, larger negative number, pretty large negative number, right? If I were to plug in all these 9s, I'm not going to waste everyone's time doing that, obviously. Okay, I'm going to get some number in the millions, but it's going to be negative, right? So what does that tell us? As we're coming from the left side, we are approaching negative infinity, right? Hopefully that clears things up a little bit, all right? So that is negative infinity. The limit as x approaches 5 from the left, that is equal to negative infinity, and you can write it just like that. That's our final answer, okay? Question, what if we were coming from the right side? I'm not going to go through all the steps, right? I just want everyone to see this, right? If we were coming from the right side, we would pick a number that's to the right of 5 barely, right? 5.0000001, okay? Well, as you can see, right, if we were to pick 5.00001, that's greater than 5. That's going to give us a positive number, but it's still going to give us a very, 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 very small decimal in the numerator or the denominator, right? That tells us that as we're coming from the right side, we're going to be going off to infinity, but it's going to be positive infinity, right? So you can see how coming from the right side, we get positive infinity, right? And if you're like, I don't understand, I don't get it, okay, think of it this way, really fast, okay, the graph 1 over x, there's a reason why I've been using this example, right? Boom, boom, okay? As we're coming in from the left side of x, right? As x approaches 0, right? We'll say as x approaches 0, okay? We're coming in from the left side, oh no, boom, negative infinity, okay? You can visually see it. As we're coming in from the right side, okay? Oh, positive infinity. That's the exact same type of graph here. There's just a little bit of different, there's some reflections going on, and there's a little bit of or not reflections, but some, oh my gosh, I'm totally forgetting the terminology. Shifts, there it is, okay? Vertical, horizontal shifts, stuff like that. That's it. So it's the same type situation. Okay, someone wanted me to go over factoring examples again real quick. I'll go ahead and do that. I will start out with a really basic factoring problem, and then I'm just going to start throwing some really crazy stuff at you, because at this point, right, we gotta understand how to factor just about everything. Okay, can I factor in x from this 10? Yes or no? I will also go over 2.3, number 31. Yeah. All right, can I factor an x from this 10? Yeah, yes, I can. Oh no, why are you saying no? What do you mean no? No, no. Yes, come on. Who? Oh, especially you, Jonna. You should know this. The yes and game, right? Yesterday, right? Yes, we can, right? Expect the unexpected. There's no x. What do you mean there's no x? There's an x right here in the denominator, right? I factored an x. Oh no. Yeah, I'm sorry. That was kind of mean. I tricked everyone. Does everyone see the X now? Does everyone see how I factored an X out, right? If you still don't see it, let me know. Does everyone see it now? Yes, there it is. There it is. Good one. Right? It's possible. Is it plausible? Should we do this? No, not always. Not always. Okay. There's a reason why I had to do the factoring worksheet, because sometimes we had to factor out an X that didn't exist, right? Because what's X divided by X? That's just 1. 1 times 10 is 10, right? Again, remember, we can factor out anything, right? We can factor out anything from anything, okay? Like, that doesn't make any sense. It kind of does, right? Let's say we had 10x plus 3 all over x, okay? Can we factor out an x on the top from both of them? You bet we can, right? Let's pull out an x here, okay? Pull out an x, we're left with 10 on the inside plus 3 over x squared, right? If you're confused on how I got that, think about it from the flip side of things, right? If I multiply the x back in, I get 10x, okay, times 3x over x squared. That's just 3 over x. That gives me the original problem that I started with, right? And that's where you've got to start thinking, right? Is okay, I can do this, and I'm not breaking any rules. I'm really not. Based off of our multiplication division rules and all that other stuff, all of this checks out, right? All of it checks out. Is it tricky and a little confusing at first? Yeah. I don't expect you to get this right away. I expect you to at least understand, okay, I see where he's coming from, right? Likewise, let's go on to a different example. Okay, again, let's just start out with the number 10. Can I factor out a full binomial expression from this? You bet I can, right? X squared minus 25x, or x squared minus 25 on the top, okay? And on the bottom here, x squared minus 25, right? It's no different than multiplying by 1, right? Because I'm basically, all I'm doing, oops, that's 25 here. Okay, all I'm doing is saying top and bottom, they cancel out, we're left with just 10. Okay, what can I do from here though? Why should I do it? What's the point? Well, here you can see, all right, I can factor this even more, right? This is x plus 5, x minus 5, x plus 5 on the top, x minus 5, right? All I did was just factor it out using the reverse FOIL method. If you're not sure how I got there, type in reverse FOIL method on Khan Academy, right? Because hopefully you know how to factor some basic stuff at this point, either using the quadratic formula, reverse FOIL method, completing the square, right? All that kind of stuff. So now you can see, okay, this is still the same problem. All I did was just factor out the top, right? And then from here, right, it's as simple as, what do I want to do the equation manipulate, right? And there's going to be other stuff in like your factoring problem, especially when you get to integrals, right, where you're going to have to cancel some things out. So don't be afraid if you're still not getting this now. It'll make more sense, right? Especially where this really comes in handy is integrals, okay? For those of you that have seen integrals before, let me just talk about it briefly. If you haven't, don't worry. Don't worry if you don't understand everything that I'm about to say, okay? This is just for those of you that have taken calculus and want a brief explanation, okay? The integral, or let's say the derivative of 2x squared, or of x squared is 2x, right? What is the integral of that? Well, that is just x squared, right, plus c, right? So the integral of 2x is x squared plus c, right? We know that, okay? What if we had the integral of x, okay? We would say, oh, that's equal to x squared over 2 plus c, right? Oops, x squared over 2 plus c. So I think you can see where I'm going with this is, in order to get our original starting equation, which was just x squared plus c, we have to multiply a 2 inside, right? We got to multiply that 2 inside but on the outside, we have to multiply 1/2, and that's all, right? We can multiply numbers in and out, right? The 2's cancel, and we're still left with the original. That's all. And you'll see that when you get to your cosine sine graph. Okay, quick explanation. If you didn't get that, don't worry. You still have, well, until the end of this school semester year to figure it out. Don't worry, they're not bad. But anyways, right, that's the type of factoring that we're going to be doing in calculus, is looking at the number, let's say x. Okay, let's just deal with an x for a second. Okay, looking at x and realizing, hey, we can multiply this x by a 5, right? And by a 1/5, right? 1/5 times 5 is just 1. Okay, that is equal to x, right? But there are some really, really good applications to this when we get to solving integrals, and we have to find constants that go inside of them, and how we multiply the outside in order to solve the integral, right? So yeah, keep this in mind. If you're given with x, you can factor out anything. You can factor out a 5. If you pull out a 1/5, you multiply a 5 by the inside. If you pull out a 5, you multiply the inside by 1/5. They cancel out. We're happy. That's all factoring is. That's really all the factoring you need to know. And then just, your basic factoring skills, right? X squared plus 4x plus 4. Okay. Hopefully I wrote this out right. This is x plus 2 times x plus 2, right? If you're confused on how I did that, again, FOIL method, it's called the reverse FOIL method. So, but if you type in FOIL method factoring, okay, that will get you where you need to go. So FOIL method factoring, hopefully you've seen this in high school. I think the majority of people have, but in case you didn't and you need some help, FOIL method factoring, search on Khan Academy, or show up to office hours and we can help you out with that too, okay? All right, that is factoring. So again, one more time, can I factor out an x from this number 10, yes or no? There it is, I'm seeing a yes. Is there more yeses? Does everyone agree or disagree? Can I pull out an x from 10? There it is. All right, cool. We're all on the same page. That's awesome. Hey, if you were saying no originally, you're totally fine. All right. I hope that I didn't upset anyone by saying, oh my gosh, you're wrong, right? Obviously, if you were to ask anyone this, they'd be like, no, you're crazy. But we are crazy. We're Berkeley students. Okay, so we know we pull out an x and we are left with a 10 over x on the inside. Cancels out. We're left with a 10. Awesome. I know that's where we need to be, and it looks like we're all there now, and that's awesome. So I'm gonna look at the chat. There was one more question about 2.2 number third. No, we already did number 32. I think that's the 6th time I've said that exact phrase today. 2.2 number 32. Huh, 7. I'm kidding. Oh no, I'm not. That's horrible. Okay, 2.3 number 31. Have we done that yet? 2.3 number 31. Someone said, all right, that's fine, but how does this help me make a rocket to get to Mars? I don't know. There's a lot of, I should be careful what I say here. There's a lot of information that we are taught once and will never have to use again. However, there's a lot of information that is taught that we will be using for the rest of our lives. So it just depends. They basically have to teach everything because not everyone is doing the exact same job, right? And so you're like, how does this help me make a rocket? How does pulling out an X get me to Mars? It's not the problem solving itself. It's the thought process behind it, right? It's the ability to recognize, hey, wait a second, I can pull out, I can do anything to this, right? Because I know if I have an X plus 1 here, I divide by an X plus 1, right? And that's all. All right, I'm getting a few questions. Yes, I'll get to them real quick. The first one I think was 2.3 number 31. 2.3 number 31. And then I will do the next one in the chat, which was good point. And 2.3 number 31 and number 26 from 1.5. 26 from 1.5. Yeah. As engineers, right, we have to be good at problem solving, not solving problems. Well, yes, solving problems, but problem solving, right? Because we're going to come across problems that we haven't seen before. So, but if we have a good foundational knowledge, and if we have good problem solving and thinking skills, that's where we become great engineers, right? And that's all. Okay, 2.3, number 31. Oh, I was like, did I say it for like the 8th time? And are people going to start yelling at me? No. I'm getting there real quick. Sorry, I'm flipping through my textbook very, very quickly. 31. All right, the limit as, oh, you chose a wonderful problem that's going to take some algebra. That's all good. 2.3, number 31. Let me erase this. Okay. If you remember back to like the very first or second day, right, where I had you plugging in stuff to an equation, okay, this is the limit as x approaches 0 of x plus h cubed. Oh, not h cubed, x plus h cubed minus x cubed all over h. I want someone in the chat right now to make an educated guess based off of how this formula looks. What is our final answer going to be? Take the derivative of it if you've taken calculus before. Tell me, because this is the definition of a derivative right here. Tell me what this is going to come out to, okay? I am going to write it in approximately 5 seconds. If someone can beat me to it, I will give you a shout out. Oh, there it is. Kamani got it, 3x squared. And then Allison, close. H squared, you're on the right track, right? We're going to end up with 3x squared here. Okay, how did I know that? Because I've taken calculus. Haha. I'm just kidding. Why would I laugh? No, there is a very, very easy way to solve these problems. You're going to learn the hard way first. That's why I was laughing, because we all have to go through that horrible process of learning it the hard way. Am I going to teach you that? Of course. Am I going to show you the easy way at the same time? Probably, because there's no reason to do it the hard way and then spend all your hours just to realize, wait, derivatives are easy. Okay, so I'll make sure to get there. But for this problem, okay, start with this cubed here. Okay, we got to multiply that out. I'm going to work on that on a separate page real quick. X plus h cubed. I'm going to write it over here. Okay, x plus, I'm going to write capital H just so people don't get confused. X plus h cubed. Cool. Let's write out x plus h times x plus h times x plus h. Okay, this is all just algebra 1 skills. You can see how algebra becomes really complicated, right? But again, start with these two terms. Use the FOIL method. Okay, we get x squared plus hx plus hx. So I'm going to combine them. That's plus 2hx. Do you understand where I'm going with this, or should I slow down and explain it a little bit fast or slower? Should I slow down and explain it faster? Of course. I'm kidding. Is that okay? Am I okay to keep going? I'm going to take the silence as yes. Okay, plus h squared. Perfect. Plus h squared. Okay, boom. Now this is all multiplied by x plus h. Okay, we're going to do it again. Hopefully my math is on point. We have x cubed plus, oh no. Oh no. Okay, x cubed plus hx squared. Hx squared. Yeah, okay, yeah, that's right. X cubed plus hx squared plus 2hx squared plus 2hx squared plus 2h squared x plus 2h squared x. Yeah, plus h squared x plus h squared x plus h cubed. Okay. So that is our expression. Okay. That's just for this term up here. Okay. So we just solved it and wrote it out like that. Okay, let's go back to our problem here. It's hard because I'm working on separate pages. Okay. So we just solved out that crazy thing. Okay. Now we subtract minus x cubed from it. Okay. So if you're okay, we're subtracting minus x cubed on the top. I'm going to go back here and I'm just going to cancel out the x cubed, right? Because we have a positive x cubed here. So we have a positive x cubed here. So x cubed minus x cubed is 0. Okay. I'm going to cancel this and erase it to make this a little bit more functional. From here, I'm going to factor out an h from every single term. Does everyone see how I have an h in every single term here, right? H squared, h cubed. Cool. I'm going to factor out an h from every single one. So I'm going to rewrite it as this, okay? All of this times an h. Hold on. Let me go back here. Did I do something? So, okay, someone catch my mistake. This should be h squared x plus hx squared, right? Does someone see how this should not be plus hx squared? Because I should, no, that's right. Yeah, never mind. Sorry, never mind. Yep, yeah. Okay, I'm factoring out h. Oops, so we're left to plus 2hx squared. No, is that right? Okay, I'm confusing myself here. Why am I doing that? Factor on h. Sorry, guys. Okay, times x squared plus 2hx squared plus 2h squared, or now this is just h plus 2h plus hx plus h squared, like so. Okay. Now we have an h multiplied on the outside, right? But if we go back to our original equation, sorry, if we go back to the original like top, so that's, we're dealing with the top, we have an h on the bottom, we can cancel those h's out. So this h cancels out this h right here on the top. Okay, now we are left with this expression right here. Okay, x squared plus 2hx squared plus 2hx. Okay, now let's talk about how we can solve this. The reason why, so now we're taking the limit as x approaches 0, or sorry, as h approaches 0. My apologies. Okay. Now we can't, so now we are just left with this equation, right? The limit as h approaches 0. My problem is there should be a 3 in front of this x squared. Okay. Somewhere in my algebra, I made a very small mistake where the x squared, yeah, somewhere in my algebra, I made a mistake. So,
Wait,
yeah.
Can I ask something? Can't you just, so there's that x squared and then, okay, never mind. Because, yeah, I feel like usually, like, there's, like, the ones that you can add.
Yeah, I know. Yeah, we should be able to combine some stuff, and that's how I should get my 3x squared once I pull out the h, right?
Yeah.
In this case, right, I'm dealing with limited space, and so I think I just made a small mental error. Okay, but you should eventually get to somewhere like this. Oops. Okay, so again, I apologize. That is an algebraic mistake, but you should somehow, some way end up with 3x squared all by itself multiplied by no h's, right? You want to take the limit as h approaches 0, right? So you plug in 0 everywhere we have an h. Okay, so here's an h, right? 0 times anything is 0. Okay, you plug in a 0 here, right? That goes to 0, right? This term goes to 0. This term goes to 0. Okay, we are left with 3x squared. That is our final answer. Okay, so again, I apologize. I don't know where I made a mistake. Otherwise, I would go back and fix it. But for the sake of time, right, just go back, multiply everything out, combine like terms. Then hopefully you will get to this answer right here. Okay, you factor out an h from every single term that you can. Cancel the h's out, top and bottom. Okay, that's like step number 3. Step number 4, what's left over? 3x squared. Okay, again, I apologize. Hopefully that you're still with me and you're able to understand that where I was coming from in that situation. Okay, I'm gonna move on here. There was one more problem in the chat. There, number 26 from 1.5. Yeah, let's jump back into 1.5 really fast. And then I will talk about the intermediate value theorem again, because I want to discuss that. So we're at 1.5, number 26. Okay. Find a formula for the inverse of the function 1 minus e to the x, 1 plus e to the negative x. Perfect. Okay. Our original equation is this: 1 minus e to the negative x. Okay. That is the letter e, right? Over 1 plus e to the negative x. Okay. So this is y equals, right? How do we find the inverse? Switch the x's and the y's. Okay. This is now y. Oops. This is e to the negative y there. This is now x. Boom. Okay. I'll rewrite that. Solve for y. Now you're probably thinking, how on earth am I going to solve for y? Great question. Let's start. I always like to do okay. I could see where you would get tripped up on this problem. Question. If I multiply this side by 5 and I multiply this side by 5, have I changed the final answer? In other words, have I made this answer invalid if I multiply both sides by 5? Yes or no? So in other words, I'm okay to do that, right? I'm okay to multiply both sides by 5. Yes. Awesome, right? Same kind of thing, right? It's you're multiplying, right? If I divide 5 to the other side, right? 5 divided by 5 is just 1. Cool, I can do that. Another question. If I took the natural log, if I took the ln, okay, of this whole expression and the ln of this whole expression, have I changed anything? Yes or no? Right? I have changed something. Ooh, I'm seeing some yeses. Ooh, okay. Tell you what, let's go through this. Let's see if I can get this. All right, that's fine. Okay. Let's see if we can rewrite these e to the negative y's really fast. Okay. This is 1 minus 1 over e to the y. Okay. I'll get rid of that really fast. And this is 1 plus e to the negative y. Or I'm sorry, 1 plus e 1 over e to the y. Okay. So I can rewrite it like that. Hopefully, or is equal to x, right? There's a few different ways you could solve this. I was originally going to take the ln of both sides, but it seems that people are afraid of me doing that. So let's see if I can try and do this in an algebraic way. I have a feeling, though, that I'm going to have to end up taking the ln of both sides just so that we can find the inverse, right? Here's the thing. Ooh, do I want to just do it and see where it takes me, right? Because I kind of want to take the ln of both sides and see where it takes us. But if you don't want me to, I don't have to. We'll try and solve this algebraically, but it'll get really messy. Did I assign this? I did assign this. Ooh, nice. So if you got it right, great job. If you didn't, that's okay. Let's see here. So we have, do I want to multiply it to the bottom? Tell you what, let's just take the ln of both sides and see where it gets us. Sound good? So I'm going to rewrite this as e to the negative y, and this is e to the negative y. You'll see why in just a second. What happens if I take the ln of both sides, okay, respectively? Okay, let's focus on the left side for a second, okay? Do you remember our natural log rules, right? Our log property rules. In other words, this is technically saying this is the ln of 1 minus e to the y, right? Minus the ln of 1 plus e to the y, e to the negative y, right? Is equal to ln of x. You see how I rewrote that just like so? Hopefully everyone's seen that a little bit. Okay. Again, now I can rewrite these even more. Okay. So the ln of 1 minus e to the y, right? I can split that up into, can I? I think I can. Am I allowed to ln of 1 minus e to the negative y? Oops, sorry, like that. Ooh, I have to go back and check our log property rules really fast. This should give us divide it. Yes, right? Ln of 1 minus e to the negative y. That should give us, well, I don't want to divide it because that'll just take us back to our original problem. So I don't know why this is tripping me up so bad. It's probably because I'm exhausted. Tell you what. I think this is on the right track. For people that did solve it, is this the process that you used, or did you use a much easier way? Because if this is the way that you solved it, divide it. Okay, what am I dividing? Divide what? So the reason why I'm doing this way is because this is how you have to solve like very complicated expressions, right? You basically, if you have e to this e to the negative y, or e to the y, anything e to the anything, to get rid of those e's, you take the natural log of it, and then you use your natural log rules. ln of 1 minus e to the negative y. I believe that should be, let's see here. If you can get to here, good. Tell you what, if you want to stay after, then we can solve it together, okay? But that is how you get this problem started. The reason why is because I just have to take a quick second to search it up, but I'm pretty sure this is on the right track, okay? Otherwise, I will get to that in just a second. Also, make sure to keep in mind that the homework solutions will be posted hopefully by the end of this week. So stay tuned for that. But yeah, that next problem, I will go ahead and solve it after class because I want to get to the mean value theorem really quickly. Everyone's like, great. Zach doesn't know how to solve his own homework problems that he gave us. Fair enough. Fair assumption. Get rid of the denominator first and then use ln. Yeah, that's where I was going with that. That's what I was thinking actually was you basically, yeah, that's good. That's a good point. So I will talk about it in just a second. Tell you what, I will go through and walk you through that example, and I will post that example only on YouTube. How about that? So that way everyone will be on the same page. I just want to go back quickly to the intermediate value theorem, right? We had f of a, f of b, and we said there is some number between f of a and f of b, right? This is f of b. And we know that there's some number between f of a and f of b. It's a number n, right, at the point C. So this is A, this is B, okay? We know that f of C, as long as it is continuous from A to B, okay? We know that there is a number n that exists between A and B, right? Because if our graph does something like this, right, we know there's a number, oops, sorry, I drew that wrong. We know, let's do something like that, there we go, okay? At f of C, okay, there's a number n right there. Does everyone see that, right? It makes logical sense. Between 2 points, right, if it's continuous, there's that middle point. Cool. How do we apply this? Great question. Let's look at 4x cubed minus 6x squared plus 3x minus 2. I know. I'm not going to graph it. I'm going to show you how we can use the mean value theorem to basically solve for roots, right? So this is 4x cubed minus 6x squared plus 3x minus 2, right? And it wants us to prove using the intermediate value theorem that there is a root to the equation, right? So use the intermediate value theorem, the IVT, okay, to prove that there's a root. What is a root? That just means that the x-axis, right? It crosses the x-axis at some point, and that point there, in other words, there's a 0 somewhere. It crosses the 0 point, right? Y equals 0. So how do we do this? Let's plug in some numbers, okay? Let's say A is equal to 1, right? And let's say B is equal to 2. Okay, let's plug in f of A, right? F of A equals 1 times, so that's, I'm just going to plug it into all the x's, right? So that is 4 minus 6 plus 3 minus 2, right? I just plugged in 1 to the equation. 4 minus 6 is negative 2, minus 2, that's negative 4. So this is negative 1. Okay, this gives us negative 1 right here. F of A is negative 1. Let's plug in B, okay? If you plug in B, all right, I'm not going to do it, right? But f of B, okay, you can go back and if you want to, or if you trust me, okay, when you plug in B and B equals 2, all right, you get f of B is equal to positive 12, okay? Is this function continuous everywhere? Is the domain continuous everywhere? Yes or no? Right? There's nothing in the denominator, it's continuous everywhere. Does everyone see that? Everyone is dead asleep in chats. All right, cool. Thank you, Stephanie. All right, thank you, Jonna. Perfect. All right, cool. I just wanted everyone to, yeah, thank you, Don. Okay. I know, we're almost at the end of class. Hang with me 2 minutes. The example's almost done, okay? We plugged in f of a. We picked 2 points, all right? We said a, b, all right? We got -1, we got -12. Conceptually, what is this telling us, okay? Let's say this is our graph right here, okay? And this is f of x, okay? From a to b, all right? We are going from, let's say a is 1, okay? That's 1, this is 2, okay? From a to b, the graph is doing something like this. Oops, that is a b, okay? Coming from -1 here, we cross at some point. Why? Because b is at +12. Okay, what does that tell us? From a to b, there's a point right in between those. There's a root, right? There's a root between a and b. Okay, what is that root? We don't know. We have to do a little bit more to solve out. Okay, we could try and approximate it, right? But in terms of the intermediate value theorem, right? Use the intermediate value theorem to prove that there's a root somewhere in this equation. Okay, we just proved it. We said f of a, right? We said f of a is negative, right? Is negative. We said f of b is positive. Okay. By the intermediate value theorem, right? By the intermediate value theorem, right? There exists at least one point, right? By the intermediate value theorem, there is at least one point, okay? There's at least one point where the graph is equal to 0, where y is equal to 0. Therefore, we have one root, at least one root. Okay, that's all you have to do. And one more thing to note, because the domain is all real numbers. Okay, that is how you use the intermediate value theorem to prove that roots exist. Get used to the intermediate value theorem. It's going to show up a lot, especially with absolute value tests, all that stuff. So, okay, other than that, yeah, that's all I have for today. Great job reviewing, and thank you for coming with questions. Sorry I wasn't able to get that one question. It's just because I have not seen that in probably 2 years. If anything, that's a good thing, right? Because that just means that you won't have to do problems like that when you get into your higher level calculus classes. I will, however, make a YouTube video just solving that problem and explaining it in detail. So check the YouTube channel for that. So I will probably upload that today in case you were wondering. That's awesome because there's still 50 of you here. So I know that at least 50 of you heard that message. Otherwise, if I'm seeing the emeralds again, or if I'm seeing the emeralds today, I will see you later. What's the YouTube channel again? Let me copy paste the link really quick. I'll send you the earliest link, and I'm typing the YouTube channel link in the chat to everyone in 3, 2, 2.5. That's going up. 1.5. There we go. 1. All right. Boom. There it is. That's the link. All right. I'm going to stop the recording here.